Hello there and welcome to the Sleepy Orbit channel. Tonight's journey takes us to the very heart of the Earth, to the mountains that breathe fire, to the hidden cracks where molten rock rises, and to the places where the ground itself can come alive in an instant. Volcanoes are not just impressive. They are powerful forces that can shake the planet, cool the entire world, or even build whole new islands overnight. Some eruptions have been heard thousands of miles away. Some send rivers of lava racing faster than a car, or clouds of ash that darken the skies of distant continents. On other planets, volcanoes reach heights taller than Mount Everest or spray ice and water into the vacuum of space. They remind us that planets, whether Earth, Mars, or far beyond, are restless and alive. If you enjoy these gentle journeys, consider liking and subscribing, or share a thought in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, you don't need to do anything at all. Just let yourself settle in, feel your breathing slow, and let your thoughts drift as lightly as ash on the wind. Now, let's begin. A single volcano once made the entire planet colder for a year. In 1815, Mount Tambora in Indonesia erupted with such force that it changed the climate of the entire Earth. Ash and sulfur shot high into the stratosphere where winds carried them around the globe. This cloud blocked enough sunlight to lower temperatures worldwide. Crops failed in Europe. Famine spread through Asia. And in North America, the year became known as the year without a summer. Frost struck in June, snow fell in July, and harvests withered in the fields. The eruption was the largest in recorded history, releasing more energy than millions of nuclear bombs. Yet the mountain itself is not widely known outside geology. It is a reminder that a single volcanic event can ripple through the atmosphere and touch lives far away, long after the fire and ash have faded from view. The scale of Tambora's eruption defies ordinary imagination. Located on the island of Sumbawa in the Indonesian archipelago, Tambora had been dormant for centuries, its magma chamber slowly refilling with volatile-rich silicic magma. When the pressure finally exceeded the strength of the overlying rock, the volcano exploded with a violence unmatched in human history. The eruption column rose over 43 kilometers into the atmosphere, well into the mesosphere, ejecting an estimated 160 cubic kilometers of material. To put this in perspective, that volume could bury the entire state of Rhode Island under nearly 400 feet of solid rock. The caldera that formed collapsed inward by over a kilometer, leaving a crater so vast it could hold a small city. But it was not the immediate destruction that made Tambora legendary. It was the global climate response. The sulfur dioxide released, over 100 million tons, combined with atmospheric water vapor to form a fine mist of sulfate aerosols. These microscopic droplets, suspended 20 miles above the Earth's surface, reflected incoming solar radiation back into space. The result was not a sudden freeze, but a slow, creeping dimming of the sun. Global average temperatures dropped by 0.4 to 0.7 degrees C, but regional effects were far more severe. In Switzerland, grain prices soared as wheat rotted in the fields. In Ireland, food riots erupted as potatoes failed to mature. In China, the monsoon patterns shifted, causing droughts in the north and floods in the south. Families boiled grass and tree bark to stave off starvation. Artists in London and New York painted skies glowing with unnatural reds and purples, unaware that they were witnessing the lingering veil of a volcano half a world away. Tambora did not just erupt, it rewrote the weather, disrupted economies, and altered the course of human history. It stands as a stark testament to the fact that Earth's systems are not isolated. They are woven together by invisible threads of air, chemistry, and heat. The eruption of Krakatoa was so loud it circled the Earth 4 times. In 1883, the Indonesian volcano Krakatoa exploded with a sound so intense it shattered eardrums 40 miles away. The pressure wave rippled outward, circling the globe not once, but 4 separate times, recorded on barometers across continents. Sailors at sea, thousands of miles distant, reported hearing what they thought was cannon fire. Closer to the island, entire coastlines were reshaped by tsunamis, and tens of thousands of people lost their lives. The sky filled with ash and sunsets turned crimson for years. Artists painted strange blood-red horizons without realizing they were witnessing the lingering signature of Krakatoa. The eruption was a global event, one that showed the world how a single volcano could reach into every corner of the planet, not only with sound, but with ash, with waves, and with light itself. The physics of Krakatoa's sound remains one of the most extraordinary phenomena in recorded history. The initial blast generated a pressure wave that traveled at the speed of sound, approximately 767 miles per hour at sea level. But high in the atmosphere, where the air is thinner and colder, sound travels slower, allowing the wave to persist and refract around the planet's curvature. Barometric stations in London, Berlin, Washington, D.C., and Sydney all recorded the same distinct spike in atmospheric pressure, not just once, but repeatedly as the wave bounced between the Earth's surface and the upper atmosphere. 4 complete circuits in 5 days. The energy released was equivalent to 200 megatons of TNT, over 13,000 times the yield of the Hiroshima atomic bomb. But it was not just the sound that reshaped the world. The collapse of 2/3 of the island into the sea displaced an estimated 21 cubic kilometers of water, generating tsunamis over 100 feet high that devastated 165 coastal villages. More than 36,000 people perished. For years afterward, global temperatures dropped by 1–2 degrees C, and vivid sunsets, caused by the scattering of light through volcanic aerosols, inspired poets, painters, and dreamers across the globe. Krakatoa reminded humanity that Earth speaks in a voice that can be heard across oceans, that a single island can echo through time and space, and that the line between local disaster and planetary event is thinner than we imagine. Pyroclastic flows can race faster than a jet plane taking off. A pyroclastic flow is one of the most dangerous volcanic hazards. It is a searing avalanche of ash, gas, and shattered rock that rushes down the slopes of a volcano. Temperatures inside can exceed 1000 degrees F. The mixture is so heavy it hugs the ground, and so fast it can reach speeds of hundreds of miles per hour, faster even than a jet during takeoff. Nothing in its path can survive. It was a pyroclastic flow that buried Pompeii under Mount Vesuvius, and another that destroyed the city of Saint-Pierre on Martinique in 1902. Witnesses described the flow as a roaring wall of fire and dust, appearing almost instantly. Scientists studied them with drones and models because no one could possibly survive inside one. Pyroclastic flows are the reason so many volcanoes are not just dangerous. They are nearly impossible to escape once they erupt. These flows are not simply rivers of hot ash. They are complex, turbulent mixtures of superheated gas and fragmented rock that behave like dense, fast-moving clouds. They form when an eruption column collapses under its own weight or when a lava dome explodes, sending a cascade of material down the volcano's flanks. Because they are denser than air, they follow the terrain like water, pouring into valleys, racing around bends, and climbing small hills with terrifying momentum. Their speed is deceptive. They often arrive with little warning, giving victims only seconds to react. The heat alone is enough to incinerate organic matter instantly, while the force of the flow can flatten forests and demolish concrete structures. In Pompeii, the first pyroclastic surge reached temperatures of 300 degrees C, 572 degrees F, killing residents in under a minute through thermal shock and suffocation. In Saint-Pierre, the 1902 flow moved at over 300 mph, extinguishing all life in the city within 2 minutes. Only a handful of survivors remained, including a prisoner locked in a stone dungeon beneath the town's square. Today, modern monitoring systems can detect the precursors to pyroclastic flows, such as dome growth or seismic tremors. But once they begin, escape is nearly impossible. They are nature's ultimate expression of sudden, unstoppable fury, a reminder that some forces on Earth demand not just respect, but absolute distance. Some lava burns hotter than molten steel. Lava is molten rock, and depending on its chemical makeup, it can vary greatly in temperature. The hottest types, known as basaltic lava, can reach more than 100 degrees F, far hotter than steel when it is forged. At these temperatures, the rock glows a brilliant orange or white and can melt almost anything it touches. The air above it shimmers with heat waves, and even at a distance, the radiating warmth is overwhelming. Yet not all lava is so fast and fluid. Some types are cooler, thicker, and creep along in slow, glowing fronts. For scientists, lava offers a chance to watch the planet's interior spill onto the surface. For people nearby, it is both beautiful and terrifying, a glowing reminder that the Earth beneath us is still a furnace burning away in silence until it chooses to rise. The temperature of lava is dictated by its composition. Basaltic lava, rich in iron and magnesium, erupts at 1800 degrees F to 200 degrees F and flows like thick syrup, capable of traveling miles before cooling. In contrast, rhyolitic lava high in silica erupts at lower temperatures, around 200 degrees F. but is so viscous that it barely moves, instead piling up into steep domes that can explode under pressure. Andesitic lava falls in between, forming the classic stratovolcanoes like Mount St. Helens, but even the cooler lava is hotter than a blast furnace used in steel mills, which typically operates around 1,600 degrees F. When basaltic lava meets water, it can trigger violent steam explosions. When it flows over asphalt, it causes the road to bubble and ignite. Trees don't just burn, they are vaporized in seconds. Yet, for all its destructive power, lava is also a builder. It creates new land, seals cracks in the Earth's crust, and over millennia forms the foundation of islands, mountains, and continents. To witness a lava flow is to see geology in real time, the slow, patient work of planetary construction played out in fire and light. Olympus Mons on Mars is a volcano the size of France. On the red planet Mars sits the largest volcano in the solar system. Olympus Mons is nearly 16 miles tall, more than twice the height of Mount Everest, and so wide it could cover the entire country of France. If you were standing on its slopes, they would seem gentle because the mountain stretches outward for hundreds of miles. Its base is bordered by cliffs taller than any on Earth, and its summit holds a crater the size of a small country. Olympus Mons is thought to have erupted for hundreds of millions of years long ago, when Mars was more geologically active. Today it is quiet, perhaps extinct, yet the sheer scale of it makes Earth's greatest volcano seem tiny. Olympus Mons is proof that planets can build mountains beyond anything we could imagine, monuments of fire and stone that dwarf our world's tallest peaks. What makes Olympus Mons so immense is the absence of plate tectonics on Mars. On Earth, tectonic plates drift over hotspots, creating chains of volcanoes like the Hawaiian Islands. But on Mars, the crust remained stationary over a long-lived mantle plume, allowing lava to erupt in the same location for eons. Layer upon layer accumulated, building a shield volcano of staggering proportions. The caldera at its summit is actually a complex of nested craters, each formed by successive collapses as magma chambers emptied. Radar and orbital imagery reveal lava flows that are remarkably smooth, suggesting they moved slowly and cooled gradually in Mars' thin atmosphere. Though no longer active, Olympus Mons stands as a silent monument to a time when Mars was geologically vibrant, a world capable of fire, not just ice. Its existence challenges our Earth-centric view of volcanism and reminds us that planetary processes operate on scales that can defy imagination. One eruption created an ash cloud that grounded planes worldwide. In 2010, Iceland's Eyjafjallajökull volcano erupted in a series of ash-spewing events that would have seemed small in past centuries. But in the modern age, it disrupted something unexpected: air travel. Volcanic ash is made of microscopic shards of glass and rock sharp enough to sandblast airplane windows and clog jet engines. When Eyjafjallajökull erupted, its ash clouds spread across Europe. Airspace was shut down for days, stranding millions of passengers. Airlines lost billions of dollars, and scientists scrambled to map the drifting particles with satellites. It was a reminder that volcanoes can affect us in new ways, not just with local destruction, but by touching the delicate systems that connect the world. The eruption was modest compared to Tambora or Krakatoa, but its impact on modern society was enormous. Even a small volcano can reach across continents in surprising ways. The disruption was unprecedented. For 6 days in April 2010, European airspace was closed from Ireland to Russia, grounding over 100,000 flights and stranding 10 million travelers. The reason? Jet engines operate at temperatures exceeding 400 degrees C, hot enough to melt volcanic ash into a glassy sludge that coats turbine blades, disrupting airflow and causing engines to stall. Unlike sand or dust, volcanic ash is hard, abrasive, and chemically reactive. Even low concentrations, just a few milligrams per cubic meter, can cause catastrophic failure. At the time, there was no agreed-upon safety threshold for ash exposure, so authorities erred on the side of caution. The event exposed a critical vulnerability in global aviation. Our skies are fragile, and a single volcano in a remote corner of the world can bring international travel to a standstill. In the aftermath, new protocols were developed, including ash concentration thresholds and real-time monitoring networks. But the lesson remains. In our interconnected world, even a minor eruption can have major consequences. Mauna Loa is so heavy it actually bends the Earth's crust. Hawaii's Mauna Loa is the largest volcano on Earth, and when measured from base to summit, it is also the tallest mountain in the world, rising more than 33,000 feet from the seafloor. It is so massive that its weight presses the crust downward, creating a vast depression in the ocean floor. This sag is called isostatic adjustment, and it means TH. At Mauna Loa is not just a mountain sitting on the Earth. It is a mountain reshaping the Earth beneath it. The volcano covers more than half of the big island of Hawaii. It has erupted dozens of times in recorded history, and though it is monitored closely, it remains active. For those who live nearby, Mauna Loa is both a home and a reminder that the ground underfoot is not fixed, but bending under the sheer weight of a mountain made of fire. Isostatic adjustment is the process by which the Earth's crust responds to surface loads, much like a mattress sinks under the weight of a person. Mauna Loa's mass, estimated at 400 billion tons, has depressed the Pacific Plate by several kilometers, forming a moat-like moat around the island. As the volcano continues to erupt and grow, this depression deepens, subtly altering local sea levels and gravitational fields. Scientists measure this flexure using GPS and satellite radar, revealing that the island is still sinking at a rate of a few millimeters per year. This ongoing deformation is a quiet but constant reminder that even the most solid-seeming land is in motion, responding to the immense forces of geology. Mauna Loa's eruptions are typically effusive, rivers of fluid lava that flow for weeks, but its potential for explosive activity remains. Its flanks are cut by deep faults that could collapse during a major quake, triggering tsunamis. Thus, Mauna Loa is not just a mountain, it is a dynamic system, constantly reshaping itself and the ocean floor beneath it. Stromboli has erupted almost non-stop for 2,000 years. On a small island off the coast of Italy, the volcano called Stromboli has been erupting so regularly that sailors once used it as a natural lighthouse. Every few minutes, fountains of lava spurt into the air, throwing glowing rocks down its slopes. This pattern has continued for thousands of years, earning Stromboli the nickname, the Lighthouse of the Mediterranean. The eruptions are relatively small compared to catastrophic blasts like Krakatoa, but their constancy is remarkable. To stand nearby at night is to watch fire leap endlessly from the earth, as though the planet itself is breathing. Stromboli is a rare example of a volcano that has been active for human history in its entirety. A steady reminder of the restless forces below. People live on the island still, accustomed to its glowing breath, knowing that fire has always been part of their horizon. Stromboli's eruptions are driven by a unique plumbing system. Magma rises slowly from depth, but as it nears the surface, gas bubbles accumulate in a shallow chamber. When pressure becomes too great, the gas bursts through the lava, ejecting blobs of molten rock up to 300 feet into the air. This process, known as Strombolian activity, occurs every 10 to 20 minutes, with metronomic regularity. The volcano's cone, built from layers of ash and scoria, is remarkably stable, allowing continuous eruption without major collapse. Local residents have learned to live with this rhythm. Children play near the slopes, farmers tend vineyards in the fertile soil, and tourists hike to the summit at dusk to witness the nightly display. There is no fear, only familiarity. Stromboli teaches us that volcanoes are not always agents of destruction. They can be companions, landmarks, and even guides. Its steady pulse is a heartbeat for the island, a symbol of endurance in a world of constant change. Entire new islands have risen from the ocean in a single eruption. When magma bursts upward through the seafloor, it sometimes builds entirely new land. In 2013, an eruption near Japan created an island that fused with Nishinoshima, growing larger each year. In 1963, Surtsey erupted off the coast of Iceland, creating an island where scientists could watch life slowly take hold on fresh volcanic rock. These islands are fragile at first, made of ash and soft stone. But over time, they can harden into permanent land. Birds arrive, plants begin to grow, and eventually ecosystems take shape. The birth of an island is a rare chance to watch geology in action, creation instead of destruction. To see land rise where once there was only ocean is to witness one of the Earth's most dramatic transformations. New islands remind us that our planet is not fixed, but always building and remaking itself. Surtsey, in particular, became a natural laboratory for studying primary succession, the process by which life colonizes barren land. Within months, mosses and lichens appeared, carried by wind and birds. Within a year, the first vascular plant took root. Today, Surtsey hosts over 69 plant species, 89 bird species, and even seals that pup on its shores. The island is now a UNESCO World Heritage Site, protected from human interference to allow science to observe nature's slow, patient work. Similarly, the island born near Nishinoshima has grown from a 200-meter wide vent to over 2.7 square kilometers in less than a decade, swallowing its older neighbor and forming a single stable landmass. These events are not rare. They occur every few years somewhere on Earth, but they are seldom witnessed in real time. They remind us that land is not eternal. It is created, eroded, and reborn in an endless cycle of fire and water. Lightning can strike inside volcanic ash clouds like a storm of fire. When a volcano erupts, it throws enormous amounts of ash and rock into the sky. Inside those clouds, particles collide and rub together, building up electrical charge, just like in a thunderstorm. The result is volcanic lightning, bolts that flash through the ash, sometimes hundreds of times a minute. The sky glows with eerie light, illuminating plumes that can rise miles into the atmosphere. Pilots have described the sight as flying past a storm made of fire. Unlike regular lightning, volcanic lightning happens in darkness inside ash where it cannot always be seen from the ground. Scientists use it as a tool because electrical activity often signals how strong the eruption has become. For those watching, the sight is unforgettable. A storm inside a storm where Earth's fury becomes not only hot and violent, but lit with its own sudden fire. Volcanic lightning forms through a process called triboelectrification. Friction between ash particles strips electrons, creating positive and negative regions within the plume. When the voltage difference becomes too great, lightning discharges bridge the gap. These strikes can occur within the eruption column, at the base of the plume, or even high in the stratosphere. High-speed cameras have captured intricate networks of electrical channels branching through ash, resembling neural pathways or river deltas. Beyond its visual drama, volcanic lightning serves as an early warning system. The frequency and intensity of strikes correlate with eruption vigor, allowing scientists to estimate ash output even when visibility is poor. In this way, the volcano speaks not just in ash and sound, but in light, a language written in electricity and fire. Obsidian blades made from volcanic glass are sharper than scalpels. When lava cools almost instantly, it can form volcanic glass called obsidian. Unlike ordinary rock, it has no crystals inside, just smooth, solid glass. Humans have used it for thousands of years to make tools and weapons. Obsidian blades can be sharper than any metal knife, so sharp that even modern surgeons have tested them for use in delicate operations. Under a microscope, a steel blade looks jagged at the edge, but obsidian's edge is nearly perfect at the molecular level. Ancient cultures prized obsidian not just for its sharpness, but for its beauty, jet black, sometimes with hints of rainbow sheen. It forms in volcanic areas like the highlands of Mexico or the slopes of the Andes. A piece of obsidian is more than just stone. It is frozen fire cooled so suddenly that lava turned into glass waiting to be shaped by human hands. The molecular precision of obsidian edges, often less than 3 nanometers thick, makes them ideal for cutting biological tissue with minimal trauma. In the 1970s, surgeons experimented with obsidian scalpels in eye and cosmetic surgery, noting cleaner incisions and faster healing. Though not widely adopted due to brittleness and regulatory hurdles, the material remains a marvel of natural engineering. For ancient Mesoamericans, obsidian was more than a tool, it was sacred. The Aztecs crafted mirrors, ritual knives, and ceremonial masks from it, believing it held the power to reveal truth and channel divine energy. Today, geologists study obsidian flows to date eruptions, as the glass slowly crystallizes over time in a process called hydration rind formation. Each shard carries a story, not just of fire and cooling, but of human ingenuity and reverence. Pumice rock from the eruptions can float for months across the sea. Pumice is a type of volcanic rock that forms when gas-rich lava cools so quickly it traps bubbles inside. The result is stone that is so light and porous it can float. After some eruptions, entire rafts of pumice drift across the ocean, stretching for miles. These floating fields have been spotted from satellites slowly moving with the currents. Eventually, pumice rafts break apart and sink, but not before traveling vast distances. Sometimes they even carry seeds, corals, or tiny animals acting as floating ecosystems. In ancient times, pumice was used as an abrasive, and even today it finds uses in cleaning and construction. To hold a piece feels strange, solid rock, but so light it bobs on water. It is one of the few times when something born of fire can take to the sea, carried along as though it weighed almost nothing at all. The 2012 Hava Seamount eruption in the South Pacific produced a pumice raft covering 400 square kilometers, the size of a small city. It drifted for over a year, traveling from New Zealand to Australia, where it washed ashore in white, porous sheets. Marine biologists discovered that these rafts serve as temporary habitats for barnacles, algae, and even juvenile fish, effectively seeding distant coastlines with life. Pumice's porosity allows it to absorb organic matter and nutrients, making it a mobile incubator for pioneer species. In this way, volcanoes do more than reshape land. They connect ecosystems across oceans, acting as unsung agents of biological dispersal. Some eruptions under ice can melt glaciers in hours. When a volcano erupts beneath a glacier, the results can be dramatic. Heat from the rising magma melts ice at astonishing speed, releasing torrents of water that burst outward as sudden floods. In Iceland, these events are called jökullaups, glacial outburst floods triggered by fire beneath ice. Entire rivers can form in hours, rushing across the land and sweeping away bridges, roads, and farms. Beneath the ice, the lava cools quickly, trapping strange formations of glassy rock. Scientists study these hidden eruptions to understand how volcanoes behave under extreme conditions. For the people who live near them, the danger is real. Fire may be hidden by the ice, but its power is no less destructive. To imagine an eruption that never breaks the surface, yet can melt miles of ice above it, is to realize how much energy still surges beneath our world. The 1996 Gjalp eruption beneath Iceland's Vatnajökull glacier melted 3 cubic kilometers of ice in less than 2 weeks, triggering a Jökullaup that carried 50,000 cubic meters of water per second, more than the Amazon River. The flood carved new canyons, moved boulders the size of houses, and destroyed a major highway. Yet the eruption itself was invisible from the surface, detected only by seismic tremors and satellite thermal anomalies. These subglacial events are among the most challenging to monitor, requiring a combination of ice-penetrating radar, GPS, and gas sensors. They remind us that volcanoes operate in all environments, underwater, under ice, in deserts, and on ocean floors, and that their power is often hidden until it breaks free. Pompeii was buried alive in less than a single day. In 79 CE, Mount Vesuvius erupted with terrifying force, sending a plume of ash, gas, and rock high into the sky. The Roman city of Pompeii, just a few miles away, was quickly overwhelmed. Roofs collapsed under the weight of ash. Pyroclastic flows surged down the mountain, smothering the city in searing heat. Thousands of people were trapped, many frozen in their final moments. The city was lost for centuries, buried beneath layers of volcanic material. When archaeologists rediscovered Pompeii in the 18th century, they found streets, houses, frescoes, and even loaves of bread still in ovens, all preserved by the ash. Today, Pompeii is a window into Roman life, not only a tragedy, but also a time capsule. The eruption reminds us how suddenly a volcano can change history, destroying in hours what had taken generations to build. The preservation was miraculous. The ash and pumice that buried Pompeii created molds around organic material, bodies, furniture, even food. When archaeologists poured plaster into these voids, they recovered hauntingly lifelike casts of victims caught in their final acts. A mother shielding her child, a guard at his post, a dog straining at its leash. The city's layout, its graffiti, its plumbing, all frozen in time. Pompeii is not just a ruin, it is a conversation with the past, made possible by the very force that ended it. It stands as the ultimate warning that civilization is fragile and geology is patient. The Earth does not sleep, even in its quietest moments, far below the surface where sunlight never reaches, a slow, patient fire stirs. This fire is not the chaotic blaze of a forest inferno, but something older, deeper, a molten river of rock flowing through channels carved over millions of years. It is this hidden heat that gives volcanoes their power, their purpose, and their paradox. They destroy, yes, but they also build. They erase, but they also create. And in their most generous moments, they make life possible. Consider the Ring of Fire, a vast, horseshoe-shaped scar that wraps around the Pacific Ocean, home to 3 out of every 4 of Earth's active volcanoes. From the snow-capped cone of Mount Fuji in Japan to the smoldering slopes of Mount St. Helens in North America, this restless boundary marks where tectonic plates collide, slide, and dive beneath one another in a process called subduction. As one plate plunges into the mantle, It carries water-rich minerals deep underground, where heat and pressure release steam that melts the overlying rock, creating magma that rises to feed volcanoes above. This is not chaos. It is a planetary recycling system, old crust consumed, new land forged, continents reshaped over millions of years. For the millions who live along this rim, volcanoes are both home and hazard, woven into culture, cuisine, and daily life. In Japan, over 100 active volcanoes dot the archipelago, a direct result of the Pacific Plate subducting beneath the Eurasian Plate. Mount Fuji, iconic and serene, last erupted in 1707, blanketing Edo, now Tokyo, in ash. Though quiet for centuries, it is far from extinct. Scientists monitor its flanks for swelling, gas emissions, and seismic tremors, knowing that pressure builds silently beneath its snow. Yet, despite the risk, people climb Fuji every summer. They build shrines at its base. They paint it in watercolors and write poetry about its perfect symmetry. For them, the volcano is not just a mountain. It is a spiritual presence, a reminder of impermanence and beauty. And the land it has shaped, rich in volcanic soil, feeds rice paddies, tea plantations, and orchards, proving once again that fire and life are deeply entwined. Similarly, in Italy, three of the world's most famous volcanoes, Vesuvius, Etna, and Stromboli, have shaped civilization for millennia. Vesuvius, which buried Pompeii in 79 CE, still looms over Naples, a sleeping giant watched by millions. Mount Etna, Europe's largest active volcano, has erupted for over 2,000 years, its slopes layered with lava flows that support vineyards, citrus groves, and almond trees. And Stromboli, the lighthouse of the Mediterranean, has erupted so steadily for 2,000 years that sailors once used its nightly fire fountains as a navigational beacon. To stand on Stromboli's slopes at night is to watch the earth breathe, glowing rocks arcing through the dark, lava bubbling in its crater like a slow, steady heartbeat. Here, fire is not an intruder. It is a rhythm, a companion, a part of the landscape as familiar as the sea or the sky. But not all volcanoes rise from colliding plates. Some, like those in Hawaii, are born from hotspots, plumes of superheated rock that rise from deep within the mantle, punching through the crust like a blowtorch through paper. As the Pacific Plate drifts slowly over this stationary hotspot, a chain of volcanoes forms, each older than the last, each frozen in time as the plate carries it away from the heat source. Mauna Loa, the largest volcano on Earth, rises 33,000 feet from the ocean floor, taller than Mount Everest, and is so massive that its weight bends the Earth's crust beneath it, creating a depression in the seafloor known as an isostatic trough. This is not just geology. It is planetary-scale engineering, where fire reshapes the very foundation of the world. And then there is Iceland, a country built at the intersection of fire and ice. Sitting directly atop the mid-Atlantic ridge, where the North American and Eurasian plates are pulling apart, Iceland is a place where new crust is born daily. Magma rises to fill the widening gap, cooling into black lava that stretches for miles. When eruptions occur beneath glaciers, as they did in 2010 with Eyjafjallajökull. They melt millions of tons of ice in hours, triggering catastrophic floods called jökullaups that carve new river valleys overnight. That same eruption sent an ash cloud across Europe, grounding over 100,000 flights and stranding millions of travelers. It was a modest blast by geological standards, yet it revealed our vulnerability to natural systems that operate on their own terms. In Iceland, people live with this duality. Eruptions destroy, yes, but they also create fertile soil, steaming hot springs, and dramatic new landscapes that draw visitors from across the globe. For them, the land is never finished. It is always becoming. Yet the dangers are real and ever-present. In 1985, the eruption of Nevado del Ruiz in Colombia triggered a laja, a volcanic mudflow, when hot ash melted the mountain's ice cap. The resulting river of wet concrete raced down valleys at highway speeds, burying the town of Armeiro and killing 20,000 people. The eruption itself was small, but the secondary effects were catastrophic. Similarly, at Lake Nyos in Cameroon in 1986, a sudden release of carbon dioxide from the depths of a volcanic crater lake rolled down hillsides like an invisible flood, suffocating 1,700 people in their sleep. There was no explosion, no warning, just silence, and then stillness. These events remind us that volcanoes are not only about fire and rock. They are also about gas, water, and chemistry, forces that can kill without a sound. Modern science now helps us listen before the Earth speaks in fire. Volcanologists, scientists who dedicate their lives to studying these giants, use a quiet arsenal of tools to detect unrest long before an eruption. Seismographs pick up the faint tremors of magma forcing its way upward, like a slow heartbeat in the rock. Satellites measure ground swelling with radar so precise it can detect changes of just a few centimeters. Gas sensors sniff the air for spikes in sulfur dioxide or carbon dioxide, chemical whispers that magma is rising. And drones, small and nimble, fly into craters too dangerous for humans, mapping heat, cracks, and gas vents with centimeter précis. In 1991, this technology allowed the evacuation of 200,000 people before Mount Pinatubo erupted, one of the 20th century's largest blasts, saving countless lives. Volcanology has become not just a science, but a shield. But sometimes the Earth speaks through its creatures. Animals, ever intuitive, often sense eruptions before humans do. Dogs bark frantically. Birds flee their roosts. Snakes emerge from hibernation in the dead of winter, crawling uphill to escape dangers we cannot yet perceive. During the eruptions of Mount St. Helens and Mount Etna, scientists recorded unusual animal behavior days before the first explosions. Their instincts, honed over millions of years, detect subtle changes in ground tilt, gas composition, or electromagnetic fields. In this, they remind us that we are not separate from the Earth, but part of its living fabric, sensitive, when we choose to be, to its subtle rhythms. And life, against all odds, thrives in the most extreme volcanic environments. Deep beneath the ocean, along mid-ocean ridges, hydrothermal vents spew superheated, mineral-rich water into the darkness. Temperatures can exceed 700 degrees F, yet ecosystems flourish. Giant tube worms, taller than a person, sway in the current, their bodies housing bacteria that convert sulfur into energy through chemosynthesis, a process that needs no sunlight. Blind shrimp scuttle over mineral chimneys, their backs lined with light-sensing organs that detect the faint glow of thermal radiation. These are not earthly anomalies. They are proof that life does not require sunlight to exist, only heat, chemistry, and time. And volcanoes provide all three. This connection between fire and life may extend even further back to the very dawn of biology. Billions of years ago, when Earth was a hostile world of lava oceans and toxic skies, it was likely volcanic vents that provided the perfect crucible for life's first spark. Their heat, minerals, and chemical gradients may have catalyzed the formation of amino acids, the building blocks of proteins. Today's hydrothermal vents are studied as analogues for this ancient world. And if life began here, it could begin elsewhere, on icy moons like Enceladus or Europa, where hidden oceans meet volcanic heat beneath kilometers of ice. In this way, volcanoes are not just destroyers or creators of land. They are midwives of biology, offering a pathway from chemistry to consciousness. Yet for all their power, volcanoes are also deeply beautiful. Lava lakes, like those at Nyiragongo in the Congo or Kilauea in Hawaii, glow like open windows into the planet's soul. At night, their orange light casts long shadows on crater walls, pulsing with slow, rhythmic movement. Obsidian, volcanic glass, forms when lava cools so quickly that crystals cannot grow. Sharp enough to slice cells, it was used by ancient surgeons and warriors alike. Its glossy black surface, sometimes shimmering with rainbow sheen, is frozen fire made solid. Pumice, so light it floats, drifts across oceans in rafts that carry seeds, corals, and even tiny ecosystems across seas. And volcanic lightning, born when ash particles collide and generate static electricity, illuminates eruption columns with electric blue flashes, turning plumes into storm clouds of fire. And then there are the blue flames of Indonesia's Kawah Ijen, a rare phenomenon where sulfuric gases ignite upon contact with air, burning with an eerie, otherworldly glow. Miners harvest solidified sulfur by hand, carrying heavy loads from the crater, while rivers of blue fire flow beside them. It is a scene from another world, yet it is Earth, alive, strange, and breathtaking. Volcanoes have shaped not just geography, but history. The Minoan civilization may have collapsed after the eruption of Thera, modern Santorini, around 1600 BCE. The global chill after Tambora inspired Mary Shelley to write Frankenstein during a sunless summer in Switzerland. The political unrest of 1816, famine, migration, rebellion, was fueled not by ideology, but by ash in the stratosphere. Even today, volcanic activity influences climate models, aviation routes, and disaster preparedness. They are planetary forces, operating on scales that dwarf human concerns, yet touch every life on Earth. But perhaps the most profound truth is this: Earth is not static. Continents drift, mountains rise, oceans open and close, and beneath it all magma moves, patient, relentless, inevitable. Volcanoes are the visible pulse of this life. Every eruption is a reminder that the ground beneath us is not fixed, but dynamic. That change is constant. That creation and destruction are two sides of the same flame. Tonight, as you rest, imagine yourself on a quiet slope in Hawaii. The eruption has ended. The lava has cooled into black rock, smooth and warm to the touch. Stars glitter overhead. The air smells faintly of sulfur and sea. You are safe. You are small. And you are part of a planet that is still being made. You are not separate from this story. You are woven into it. The calcium in your bones, the iron in your blood, the oxygen in your breath, all were forged in the hearts of ancient stars, scattered by supernovae and delivered to a young Earth by comets and asteroids. But it was volcanoes that gave this stardust a home, releasing water vapor to form oceans, carbon dioxide to build the first atmospheres, and heat to stir the chemistry of life. You are stardust resting on living rock, cradled by a world that still breathes with fire. And that fire is not just here. It is on Mars, in the silence of Olympus Mons. It is on Io, in rivers of molten sulfur. It is on Enceladus, in fountains of salty water shooting into the void. The universe is not dead. It is alive with geology, with energy, with the slow, patient work of worlds remaking themselves. As you drift towards sleep, let the grandness of it all soften into calm. You don't need to hold every fact, every mountain, every moon in your mind. Just let the warmth of the earth beneath you remind you are part of something vast, ancient, and still unfolding. And this unfolding continues, not just in space, but in the daily life of a garden center shaped by fire and neglect. Some volcanic craters are filled with lakes so vivid they seem painted by an otherworldly hand. At Indonesia's Kawah Ijen, a crater lake glows an electric turquoise, rimmed by steaming fumaroles that hiss with sulfurous steam. By day, the water shimmers like liquid gemstone. By night, it transforms. Blue flames, not lava but burning sulfur gas, leap from cracks in the ground, casting an eerie, unearthly glow across the slopes. Miners harvest solidified sulfur by hand, carrying 200-pound loads from the crater, while rivers of blue fire flow beside them. It is a scene both beautiful and harrowing, a testament to the raw duality of volcanoes. Yet beauty can mask danger. Kawah Ijen's lake is one of the most acidic bodies of water on Earth, pH near 0, as corrosive as battery acid. The gases bubbling beneath its surface, carbon dioxide, sulfur dioxide, hydrogen sulfide, are invisible killers. In 1979, a sudden release of gas at a similar crater lake, Lake Monoan in Cameroon, suffocated 37 people in their sleep. 2 years later at Lake Nyos, just 20 miles away, a far deadlier event unfolded. On August 21, 1986, a massive cloud of carbon dioxide, 1.2 million tons, erupted from the depths of the lake, rolling down valleys like an invisible avalanche. It displaced oxygen, asphyxiating 1,746 people and 3,500 livestock in under an hour. There was no explosion, no ash, no warning, just silence, and then stillness. Today, scientists have installed degassing pipes in both lakes, slowly siphoning gas to prevent future disasters. These crater lakes are not just scenic wonders, they are time bombs of chemistry, reminding us that volcanoes can kill without fire, without sound, without spectacle. And then there are the lahars, volcanic mudflows that behave like rivers of wet concrete. When ash mixes with rain, snowmelt, or glacial ice, it forms a slurry so dense it can carry boulders, trees, and entire buildings. In 1985, the eruption of Nevado del Ruiz in Colombia was relatively small, yet it melted the mountain's ice cap, triggering a lahar that buried the town of Armeiro under 13 feet of mud. 23,000 people died, many in their beds, unaware that a wall of mud was racing toward them at 60 km/h. The tragedy was preventable. Scientists had warned of the risk weeks earlier, but evacuation plans were never implemented. Lahars can strike hours after an eruption begins, catching communities off guard. They are among the most destructive secondary hazards, water and fire fused into a single, unstoppable flood. But not all volcanic threats are sudden. Many unfold slowly, invisibly, through the air we breathe. Volcanoes release vast quantities of gases: water vapor, carbon dioxide, sulfur dioxide, hydrogen sulfide, and chlorine. Some, like water vapor, are harmless. Others are insidious. Sulfur dioxide rises into the stratosphere, where it forms sulfate aerosols, microscopic droplets that reflect sunlight and cool the planet. After the 1991 eruption of Mount Pinatubo in the Philippines, global temperatures dropped by 0.5 degrees C for 2 years. Sunsets turned crimson across Europe and North America. Painters captured skies that glowed like embers, unaware they were illustrating the breath of a volcano half a world away. Yet these same aerosols can damage the ozone layer, increasing UV radiation. And closer to the source, acid rain forms when sulfur and chlorine gases mix with atmospheric moisture. After Pinatubo, acid rain fell across Southeast Asia, bleaching forests, poisoning lakes, and corroding metal roofs. Farmers watched helplessly as crops withered under skies that seemed clear, yet carried invisible acid in every drop. Volcanic gases ripple across continents, proving that eruptions are not just local events, but planetary chemical interventions. Modern science now listens to the Earth before it speaks in fire. Volcanologists, scientists who study these giants, use a quiet arsenal of tools to detect unrest long before an eruption. Seismographs pick up the faint tremors of magma forcing its way upward. Tiny earthquakes, called long-period events, that signal fluid movement. Satellites measure ground swelling with radar so precise it can detect changes of just a few centimeters, like watching a volcano take a deep breath. Gas sensors, both on the ground and aboard drones, Sniff the air for spikes in sulfur dioxide or carbon dioxide, chemical whispers that magma is rising. And thermal cameras map heat signatures at night, revealing new lava flows or growing domes hidden in darkness. In 1991, this technology allowed the evacuation of 200,000 people before Pinatubo erupted, one of the 20th century's largest blasts, saving countless lives. Volcanology has become not just a science but a shield, yet it is not infallible. Sometimes the earth speaks through its creatures. Dogs bark frantically, birds flee their roosts, snakes emerge from hibernation in the dead of winter, crawling uphill to escape dangers we cannot yet perceive. During the eruptions of Mount St. Helens and Mount Etna, scientists recorded unusual animal behavior days before the first explosions. Their instincts, honed over millions of years, detect subtle changes in ground tilt, gas composition, or electromagnetic fields. In this, they remind us that we are not separate from the Earth, but part of its living fabric, sensitive, when we choose to be, to its subtle rhythms. And for those who cannot get close, space offers a new vantage point. From the International Space Station, astronauts have captured eruptions in real time, towering ash columns punching into the stratosphere, shockwaves rippling outward in perfect circles, lightning flashing inside plumes like storm clouds made of fire. Satellites track ash clouds across continents, helping aviation reroute flights around danger zones. Infrared sensors map lava flows at night, revealing the hottest parts of an eruption even through clouds. Orbital footage of the 2010 Eyjafjallajökull eruption showed how a modest blast could grind European air travel to a halt. 100,000 flights grounded, 10 million travelers stranded, all from a volcano most had never heard of. From space, a single eruption becomes a global signal, visible minute by minute as it evolves. These tools are not just for observation, they prepare us for exploration beyond Earth. Astronauts train on volcanic terrain because it mirrors the Moon and Mars. In Hawaii, they hike across basaltic lava fields, learning to identify pressure ridges, lava tubes, and ash layers. In Iceland, they practice sampling in steaming fumarole fields, simulating operations in extraterrestrial geothermal zones. Volcanic ash mimics lunar regolith. Lava tubes offer natural shelters from radiation. On Earth's fire-formed landscapes, future explorers learn to read the language of alien worlds, geology as a universal dialect. But volcanoes are not just destroyers or hazards. They are creators of life itself. Billions of years ago, Earth was a hostile world, oceans of lava, constant bombardment, a toxic atmosphere of methane and ammonia. Yet in the deep ocean, near hydrothermal vents, volcanic chimneys spewing superheated mineral-rich water, conditions may have been just right for life to emerge. Heat, chemistry, and constant flow created a perfect crucible for amino acids, the building blocks of proteins to form. Today, these vents host ecosystems independent of sunlight, powered by chemosynthesis, bacteria converting sulfur into energy, supporting tube worms, clams, and shrimp in total darkness. If life began here, it could begin elsewhere, beneath the ice of Enceladus, in the subsurface ocean of Europa, or even in ancient hot springs on Mars. Volcanoes, then, are not just builders of mountains. They are midwives of biology, offering pathways from chemistry to consciousness. This connection between fire and life extends to the land we walk on. Volcanic soils, known as andisols, are among the most fertile on Earth. When lava weathers over centuries, it breaks down into a rich, dark earth packed with potassium, phosphorus, iron, and trace elements. The coffee of Guatemala, the rice of Indonesia, the wine of Sicily all thrive on land born of fire. Farmers have long understood this paradox. The same forces that can bury villages in ash also replenish the soil for generations. In Indonesia, over 120 active volcanoes provide fertile slopes for 250 million people. In Japan, volcanic ash enriches rice paddies. In Italy, vineyards climb the slopes of Etna. For these communities, volcanoes are not distant hazards. They are home, heritage, and harvest. And human civilization has always walked this razor's edge. The Maya built cities in the shadow of Central American volcanoes, using obsidian for tools and trade. The Romans thrived near Vesuvius until they didn't. Pompeii, buried in 79 CE, was not just destroyed, it was preserved. Ash and pumice created molds around organic material, bodies, furniture, even bread in ovens. When archaeologists poured plaster into these voids, they recovered hauntingly lifelike casts. A mother shielding her child, a dog straining at its leash, a guard at his post. Pompeii is not just a ruin, it is a conversation with the past, made possible by the very force that ended it. It stands as the ultimate warning that civilization is fragile and geology is patient. Yet for all their power, volcanoes are also deeply beautiful. Lava lakes, like those at Nyiragongo in the Congo or Kilauea in Hawaii, glow like open windows into the planet's soul. At night, their orange light casts long shadows on crater walls, pulsing with slow, rhythmic movement. Obsidian, volcanic glass, forms when lava cools so quickly that crystals cannot grow. Sharp enough to slice cells, it was used by ancient surgeons and warriors alike. Its glossy black surface, sometimes shimmering with rainbow sheen, is frozen fire made solid. Pumice, so light it floats, drifts across oceans in rafts that carry seeds, corals, and even tiny ecosystems across seas. And volcanic lightning, born when ash particles collide and generate static electricity, illuminates eruption columns with electric blue flashes, turning plumes into storm clouds of fire. Volcanoes have shaped not just geography, but history. The Minoan civilization may have collapsed after the eruption of Thera, modern Santorini, around 1600 BCE. The global chill after Tambora inspired Mary Shelley to write Frankenstein during a sunless summer in Switzerland. The political unrest of 1816, famine, migration, rebellion, was fueled not by ideology, but by ash in the stratosphere. Even today, volcanic activity influences climate models, aviation routes, and disaster preparedness. They are planetary forces, operating on scales that dwarf human concerns, yet touch every life on Earth. But perhaps the most profound truth is this: Earth is not static. Continents drift, mountains rise, oceans open and close, and beneath it all magma moves, patient, relentless, inevitable. Volcanoes are the visible pulse of this life. Every eruption is a reminder that the ground beneath us is not fixed, but dynamic. That change is constant. That creation and destruction are two sides of the same flame. Tonight, as you rest, imagine yourself on a quiet slope in Hawaii. The eruption has ended. The lava has cooled into black rock, smooth and warm to the touch. Stars glitter overhead. The air smells faintly of sulfur and sea. You are safe. You are small. And you are part of a planet that is still being made. You are not separate from this story. You are woven into it. The calcium in your bones, the iron in your blood, the oxygen in your breath, all were forged in the hearts of ancient stars, scattered by supernovae and delivered to a young Earth by comets and asteroids. But it was volcanoes that gave this stardust a home, releasing water vapor to form oceans, carbon dioxide to build the first atmospheres, and heat to stir the chemistry of life. You are stardust resting on living rock, cradled by a world that still breathes with fire. And that fire is not just here. It is on Mars, in the silence of Olympus Mons. It is on Io, in rivers of molten sulfur. It is on Enceladus, in fountains of salty water shooting into the void. The universe is not dead. It is alive with geology, with energy, with the slow, patient work of worlds remaking themselves. As you drift towards sleep, let the grandness of it all soften into calm. You don't need to hold every fact, every mountain, every moon in your mind. Just let the warmth of the earth beneath you remind you, you are part of something vast, ancient, and still unfolding. The earth does not erupt in silence. Long before lava breaches the surface, before ash darkens the sky, before pyroclastic flows race down slopes, the planet begins to whisper. These whispers are faint, subtle, and easily missed, but to those who know how to listen, they are clear as a bell. Modern science has learned to hear these murmurs through a quiet symphony of instruments. Seismographs that feel the tremors of rising magma, satellites that watch the ground swell from space, gas sensors that sniff the breath of volcanoes, and drones that fly into craters too dangerous for human eyes. This is not magic, it is vigilance. And in places like Pinatubo, Mount St. Helens, and Eyjafjallajökull, this vigilance has saved thousands of lives. Consider the seismograph, a simple device that records the trembling of the earth. To the untrained eye, its output is just squiggles on a screen, but to a volcanologist, it is a conversation. Before an eruption, magma forces its way upward through cracks in the crust, fracturing rock and generating tiny earthquakes. These are not like tectonic quakes. They are shallower, more frequent, and often accompanied by a low, steady hum called harmonic tremor, the sound of fluid moving underground. Scientists look for patterns, a swarm of quakes clustered beneath a volcano, migrating upward over days. A sudden increase in long-period events, caused by gas and magma sloshing through narrow channels. These are not random noises. They are the Earth's way of saying, pressure is building, something is rising. In 1991, these signals allowed scientists to evacuate 200,000 people before Pinatubo erupted, one of the 20th century's largest blasts, turning a potential catastrophe into a triumph of prediction. But seismographs alone are not enough. The ground itself swells as magma inflates chambers beneath the surface, like a lung filling with air. In the past, this swelling was measured with tiltmeters, delicate instruments that could detect millimeter-scale changes. Today, satellite radar interferometry, INSAR, maps these deformations from orbit with centimeter precision. A satellite sends radar pulses to the ground and measures the time it takes for them to return. By comparing images taken days or weeks apart, scientists can create detailed maps of inflation and deflation. When Mount Etna swells, when Kilauea's summit lifts, when Yellowstone's caldera breathes, INSAR sees it all. This technology is especially vital for remote volcanoes like those in the Aleutians or the Andes, where ground instruments are sparse. From space, the Earth's unrest becomes visible, not as chaos, but as a measurable, trackable process. And then there is gas, the invisible language of volcanoes. Magma carries dissolved gases, water vapor, carbon dioxide, sulfur dioxide. As it rises and pressure drops, these gases escape, like bubbles in a shaken soda can. Gas sensors, placed on the ground or flown by drones, measure the composition and concentration of these emissions. A spike in sulfur dioxide often means fresh magma has reached shallow depths. A shift in the ratio of carbon dioxide to sulfur dioxide can reveal whether magma is still deep or nearing the surface. At Mount Etna, scientists have installed permanent gas stations that stream real-time data to monitoring centers. During the 2018 Kilauea eruption, gas sensors detected rising sulfur dioxide levels days before fissures opened in residential neighborhoods, giving residents precious time to evacuate. Gas doesn't lie. It is a chemical whisper that pressure is mounting, long before the first ash appears. Drones have revolutionized this work. Small, agile, and fearless, they fly into craters where helicopters dare not hover and humans would face toxic air, rockfall, or sudden explosions. Equipped with thermal cameras, gas samplers, and LiDAR scanners, they map lava lakes, measure vent temperatures, and track dome growth with centimeter accuracy. After a drone survey of Stromboli, scientists discovered new fractures forming along the crater rim, early signs of instability that could lead to a collapse and pyroclastic flow. In Iceland, drones monitored the 2014-2015 Holuhraun eruption, mapping lava flows in real time and helping authorities reroute roads and protect infrastructure. These machines are not replacements for scientists. They are extensions of them, nimble scouts gathering data from the most dangerous edges so people don't have to stand there themselves. And from even higher, the International Space Station, and weather satellites capture eruptions in breathtaking detail. Cameras have recorded towering umbrella clouds blooming in minutes, shock waves rippling outward as perfect circles, and ash columns punching into the stratosphere. Infrared sensors reveal the hottest parts of plumes at night. Lightning detectors map furious electrical storms inside ash clouds. Time-lapse sequences show how winds shear plumes into long filaments that stretch for thousands of kilometers. For the 2010 Eyjafjallajökull eruption, orbital footage was the only way to track the ash cloud across Europe, allowing aviation authorities to draw precise no-fly zones. Space turns a single volcano's outburst into a global signal, visible minute by minute as it evolves, proof that even the most local event can ripple across continents. This technology matters because volcanoes are not just fire, they are chemistry. When an eruption sends sulfur dioxide into the stratosphere, it reacts with water to form sulfate aerosols, microscopic droplets that reflect sunlight and cool the planet. After Pinatubo erupted in 1991, global temperatures dropped by 0.5 degrees C for 2 years. Sunsets turned crimson across Europe and North America. Painters captured skies that glowed like embers, unaware they were illustrating the breath of a volcano half a world away. These aerosols can also damage the ozone layer, increasing UV radiation at the surface. Closer to the source, acid rain forms when sulfur and chlorine gases mix with atmospheric moisture. After Pinatubo, acid rain fell across Southeast Asia, bleaching forests, poisoning lac and corroding metal roofs. Farmers watched helplessly as crops withered under skies that seemed clear, yet carried invisible acid in every drop. Volcanic gases ripple across continents, proving that eruptions are not just local events, but planetary chemical interventions. Yet beauty can mask danger. At Indonesia's Kawah Ijen, a crater lake glows an electric turquoise, rimmed by steaming fumaroles that hiss with sulfurous steam. By night, blue flames, not lava but burning sulfur gas, leap from cracks in the ground, casting an eerie, unearthly glow. Miners harvest solidified sulfur by hand, carrying 200-pound loads from the crater, while rivers of blue fire flow beside them. It is a scene both beautiful and harrowing. But the lake is one of the most acidic bodies of water on Earth, pH near 0, as corrosive as battery acid. The gases bubbling beneath its surface, carbon dioxide, sulfur dioxide, hydrogen sulfide, are invisible killers. In 1979, a sudden release of gas at a similar crater lake, Lake Monoan in Cameroon, suffocated 37 people in their sleep. 2 years later, at Lake Nyos, just 20 miles away, a far deadlier event unfolded. On August 21, 1986, a massive cloud of carbon dioxide, 1.2 million tons, erupted from the depths of the lake, rolling down valleys like an invisible avalanche. It displaced oxygen, asphyxiating 1,746 people and 3,500 livestock in under an hour. There was no explosion, no ash, no warning, just silence, and then stillness. Today, scientists have installed degassing pipes in both lakes, slowly siphoning gas to prevent future disasters. These crater lakes are not just scenic wonders, they are time bombs of chemistry, reminding us that volcanoes can kill without fire, without sound, without spectacle. But not all volcanic threats are sudden. Many unfold slowly, invisibly, through the air we breathe and the soil we walk on. Volcanic soils, known as andisols, are among the most fertile on Earth. When lava weathers over centuries, it breaks down into a rich, dark earth packed with potassium, phosphorus, iron, and trace elements. The coffee of Guatemala, the rice of Indonesia, the wine of Sicily all thrive on land born of fire. Farmers have long understood this paradox. The same forces that can bury villages in ash also replenish the soil for generations. In Indonesia, over 120 active volcanoes provide fertile slopes for 250 million people. In Japan, volcanic ash enriches rice paddies. In Italy, vineyards climb the slopes of Etna. For these communities, volcanoes are not distant hazards. They are home, heritage, and harvest. And human civilization has always walked this razor's edge. The Maya built cities in the shadow of Central American volcanoes, using obsidian for tools and trade. The Romans thrived near Vesuvius until they didn't. Pompeii, buried in 79 CE, was not just destroyed, it was preserved. Ash and pumice created molds around organic material, bodies, furniture, even bread in ovens. When archaeologists poured plaster into these voids, they recovered hauntingly lifelike casts, a mother shielding her child, a dog straining at its leash, a guard at his post. Pompeii is not just a ruin, it is a conversation with the past, made possible by the very force that ended it. It stands as the ultimate warning that civilization is fragile and geology is patient. Yet for all their power, volcanoes are also deeply beautiful. Lava lakes, like those at Nyiragongo in the Congo or Kilauea in Hawaii, glow like open windows into the planet's soul. At night, their orange light casts long shadows on crater walls, pulsing with slow, rhythmic movement. Obsidian, volcanic glass, forms when lava cools so quickly that crystals cannot grow. Sharp enough to slice cells, it was used by ancient surgeons and warriors alike. Its glossy black surface, sometimes shimmering with rainbow sheen, is frozen fire made solid. Pumice, so light it floats, drifts across oceans in rafts that carry seeds, corals, and even tiny ecosystems across seas. And volcanic lightning, born when ash particles collide and generate static electricity, illuminates eruption columns with electric blue flashes, turning plumes into storm clouds of fire. Volcanoes have shaped not just geography, but history. The Minoan civilization may have collapsed after the eruption of Thera, modern Santorini, around 1600 BCE. The global chill after Tambora inspired Mary Shelley to write Frankenstein during a sunless summer in Switzerland. The political unrest of 1816, famine, migration, rebellion, was fueled not by ideology, but by ash in the stratosphere. Even today, volcanic activity influences climate models, aviation routes, and disaster preparedness. They are planetary forces, operating on scales that dwarf human concerns, yet touch every life on Earth. But perhaps the most profound truth is this: Earth is not static. Continents drift, mountains rise, oceans open and close, and beneath it all magma moves, patient, relentless, inevitable. Volcanoes are the visible pulse of this life. Every eruption is a reminder that the ground beneath us is not fixed, but dynamic. That change is constant. That creation and destruction are two sides of the same flame. Tonight, as you rest, imagine yourself on a quiet slope in Hawaii. The eruption has ended. The lava has cooled into black rock, smooth and warm to the touch. Stars glitter overhead. The air smells faintly of sulfur and sea. You are safe. You are small. And you are part of a planet that is still being made. You are not separate from this story. You are woven into it. The calcium in your bones, the iron in your blood, the oxygen in your breath, all were forged in the hearts of ancient stars, scattered by supernovae and delivered to a young Earth by comets and asteroids. But it was volcanoes that gave this stardust a home, releasing water vapor to form oceans, carbon dioxide to build the first atmospheres, and heat to stir the chemistry of life. You are stardust resting on living rock, cradled by a world that still breathes with fire. And that fire is not just here. It is on Mars, in the silence of Olympus Mons. It is on Io, in rivers of molten sulfur. It is on Enceladus, in fountains of salty water shooting into the void. The universe is not dead. It is alive with geology, with energy, with the slow, patient work of worlds remaking themselves. As you drift towards sleep, let the grandness of it all soften into calm. You don't need to hold every fact, every mountain, every moon in your mind. Just let the warmth of the earth beneath you remind you, you are part of something vast, ancient, and still unfolding. And this unfolding continues, not just in space, but in the daily life of a garden center shaped by fire and neglect. You have journeyed tonight through 100 quiet wonders, from the first flicker of volcanic light on a newborn Earth to the silent breath of cryovolcanoes on distant moons, from the roar of Krakatoa to the gentle pulse of Stromboli's nightly fire. You have drifted through lava lakes and sulfur blue flames, through ash clouds that circled the globe and islands born in a single night. And through it all, one truth remains: everything is connected. The iron in your blood was forged in dying stars. The oxygen you breathe was cooked in red giants. The warmth beneath your feet comes from Earth's primordial heat, still flowing after 4.5 billion years. The clean water you drink exists because volcanoes outgassed an atmosphere and filled the oceans. Even the risk of a falling display unit in a garden center is tied to the same physical laws that govern pyroclastic flows and collapsing calderas: gravity, balance, momentum, consequence. You are not separate from this story. You are part of it, resting on land built by ash, breathing air shaped by eruptions, living in the long, quiet aftermath of ancient fire. But let us return now to the human realm, not as an afterthought, but as a continuation of the same planetary rhythm. Consider the quiet courage of the volcanologist who climbs a steaming slope at dawn, gas sensor in hand, knowing that magma is rising beneath their feet. Or the farmer in Indonesia who tends rice paddies on the slopes of Merapi, aware that the same soil that feeds their family could one day bury their home. Or the scientist in Iceland who flies a drone into an ash plume, mapping heat and gas so that others may be warned. These are not acts of heroism, but of care, a deep, quiet attention to the living earths. And this care must extend to places like Hollowbrook Garden Centre, a place of beauty, yes, with its hanging wind chimes, its pet store smelling of hay and clean water, its cafe with up-to-date hygiene logs. But look closer. The fire exit is blocked by trolleys full of stock. Uneven floor tiles cause workers to stumble. The hot tubs, meant to delight customers, have gone uncleaned for a month, their chlorine tablets exhausted, their walls slick with biofilm. A child ducks to avoid a wind chime that swings too low. A temporary worker limps from a twisted ankle, carrying a heavy bag of compost through a narrow aisle crowded with leaning racking. And behind it all, a manager who says, "I don't have time for that type of thing," and tolerates shortcuts to get the job done fast. This is not just poor management. It is a failure of planetary proportion, not because the stakes are galactic, but because the same principles that govern the universe also govern human safety: structure, balance, foresight, and care. The universe does not tolerate negligence. Gravity will pull a display unit down if it is stacked too high and too loosely. Heat will build in a glass-fronted room if ventilation is ignored. Water will breed bacteria if not treated. These are not opinions. They are laws written in physics, in chemistry, in biology. And when we ignore them, consequences follow, as surely as a pyroclastic flow follows a collapsing lava dome. The recent accident, a display unit falling, trapping. A worker is not an anomaly. It is the inevitable result of a system that has abandoned risk assessment, maintenance, training, and worker involvement. The only risk assessment in place is generic, outdated, and laughably trivial, mentioning paper cuts and minor bumps, while ignoring falling displays, blocked exits, and biological hazards in hot tubs. It was written by a manager with no technical competence in health and safety, and it covers only permanent workers, excluding the seasonal staff who make up half the workforce in summer. Meanwhile, workers report hazards, uneven tiles, lack of chlorine, narrow aisles, but nothing changes. They are afraid to be seen as a moaner. They skip safety steps under pressure, and when an accident happens, they simply reset the display and move on, with no investigation, no learning, no prevention. This is the opposite of how the cosmos operates. In the universe, every event is connected. A supernova seeds a cloud with heavy elements. That cloud collapses to form a star. Planets coalesce. Volcanoes outgas an atmosphere. Life emerges. Each step depends on the one before. There is no waste, no neglect, only transformation. Hollowbrook, by contrast, operates in isolation, in cosmic variance of the worst kind, not because it lacks data, but because it lacks attention. The supervisor says, "We explain things when workers start, but we do not write anything down." There are no cleaning logs for the hot tubs, no records of incident reports, no clear responsibility for fire exits. It is a world without memory, without accountability, where each day is a repeat of the last until someone is hurt. And now enforcement officers have arrived. They see the green sheen in the hot tubs. They issue an enforcement notice. They warn that more serious injuries are imminent. They demand a formal health and safety management system, not as bureaucracy, but as structure, as scaffolding, as the cosmic web that holds galaxies together. For a garden center, like a planet, must have systems. Risk assessments that are specific, reviewed, and inclusive of all workers. Worker involvement through safety committees, anonymous reporting, and consultation. Training records, not just verbal instructions. Clear roles: who is responsible for fire exits, for hot tub maintenance, for racking stability. Incident investigation, so that every near miss and injury becomes a lesson. Management leadership, a manager who attends safety meetings, who reads audit reports, who prioritizes people over speed. Without these, Hollowbrook is not a business. It is a time bomb waiting for the next collapse, the next rash, the next broken bone. And now a new initiative looms: online orders, a warehouse in the outdoor area, extended hours shift work. If poorly managed, this could worsen everything. Workers already stretched thin will be asked to lift heavy paving stones in the dark. Narrow aisles will become congested with packing stations. Fatigue from shift work will increase errors. And without proper risk assessment, training, or supervision, the next accident may not be a twisted ankle, but something far worse. Yet the opportunity is also there. This change could be a cosmic dawn for Hollowbrook, a chance to rebuild with care, to create systems that protect as well as produce, to honor the dignity of every worker, just as the universe honors the role of every atom. For you are not just a customer or a manager or a worker. You are a conscious fragment of cosmic dust, breathing air shaped by ancient volcanoes, walking on ground built by fire and time. And in that awareness lies responsibility, not as burden, but as connection. Now let us return to the stars, not to escape Earth, but to remember that fire is universal. On Mars, Olympus Mons stands silent, a monument to a world that once burned with internal fire. On Io, rivers of molten sulfur flow beneath a sky lit by Jupiter's glare. On Enceladus, fountains of salty water shoot into the void, carrying the chemistry of life into space. These are not alien phenomena. They are volcanic expressions of the same restless energy that built our mountains, filled our oceans, and stirred the first sparks of biology in hydrothermal vents. Volcanoes are not just destroyers. They are architects of possibility. Without them, Earth would be a dry, airless rock. Without them, there would be no fertile soil, no atmosphere, no water, and no life. and life once begun clings to volcanic landscapes with quiet tenacity. In Hawaii, new lava flows are colonized by lichens within years. In Iceland, Surtsey Island hosts birds, insects, and flowering plants where once there was only ash. In the deep ocean, tube worms thrive in darkness, fed by chemicals from volcanic vents. Life does not wait for perfection. It seizes the moment, the crack, the opening, and grows. So too must we. As you drift towards sleep, let the grandness of it all soften into calm. You don't need to fix every hazard ton. You don't need to map every galaxy. Just let the rhythm of your breath mirror the slow pulse of the earth, steady, resilient, alive. The universe continues its quiet unfolding. New stars ignite in hidden clouds. Light travels across eons to touch future eyes. Volcanoes exhale on distant moons. And somewhere, in the vast radiant sea of space and time, you float, warm, aware, and deeply connected. Thank you for journeying through fire and starlight with me tonight. I hope you sleep well and dream softly on the warm, restless rock of a living cosmos. Good night.